Hello class, today we're going to learn about DC circuits. Do you remember what DC stands for? That's right, direct current, current flowing in one direction. The first two terms you're going to learn is EMF and terminal voltage. EMF stands for electromagnetic force. However, it's not a force, but it's actually a voltage. A battery for voltage source all have some amount of EMF, meaning voltage. The variable we'll use for EMF is the Greek letter that looks like a curly E. All batteries, or whatever voltage source you're using, has some internal resistance. It's not perfect. So the actual voltage your circuit is receiving from the battery is called terminal voltage. In the equation below, VAB stands for terminal voltage. Little r stands for internal resistance of the battery, and you already know that I stands for current. So you should expect the terminal voltage to be less than EMF because of the internal resistance of the battery. Here's a visual figure of a battery with its two terminal voltage leads sticking out. The long vertical line next to the short vertical line is a symbol for voltage in a circuit drawing. Above it you see a curly E standing for EMF, which remember stands for the voltage of the battery. The zigzag is a symbol for resistance, and the little r above it stands for internal resistance of the battery. And lastly, VAB stands for the potential difference across the two leads, which we defined as terminal voltage of the battery. Now remember, the terminal voltage should be less than EMF. Okay, we're ready for our first example. A 65 ohm resistor is connected to terminals of a battery whole EMF is 12 volts, and whose internal resistance is 0.5 ohms. We want to calculate the current in the circuit, the terminal voltage of the battery, and the power dissipated from both resistors. We'll start with our new equation. We're trying to solve for current, but we don't know the terminal voltage. However, we can apply Ohm's law, V equals IR, and make that substitution in for terminal voltage. Big R is a resistance between the potential difference of A and B. Now we can start solving for I. To get EMF over the external resistance over the internal resistance. Now we can plug in chug to get a current of 0.183 amps. For part B, we can use the same equation to solve for terminal voltage. From there, it's just a straight plug and chug to get 11.9 volts as the terminal voltage. Notice that this number is slightly less than the EMF, and that's due to the internal resistance of our voltage source. The last step is to solve for the power dissipated by the external and internal resistance. We can use this equation, P equals I square R. Plug and chug to get power dissipated across the external resistance to be 2.18 watts and the internal resistance to only be 0.02 watts. Now, typically most problems we'll deal with, we'll ignore the internal resistance and just take the battery voltage at face value. Two new terms we'll now discuss are the resistors in series versus parallel. In the figure below, we have a circuit diagram with three resistors in series. The total amount of resistance in the whole circuit, or known as the equivalent resistance, determines the amount of current drawn out of the battery. The larger the equivalent resistance, the smaller amount of current that will be drawn out of the battery. Now for resistance in series, the current is the same value through each resistor, but the potential difference, or voltage, across each resistor is different. The highest potential is at the positive end of the battery lead, and the lowest potential is at the negative end of the battery lead. Now, we always set the lowest potential to 0, and the potential remains the same value in the circuit until it crosses a resistor. Once the current goes through a resistor, the potential drops. The amount of potential drop depends on the value of the resistor. On the figure, I place red dots at different potential values. A has the highest potential and D has the lowest potential of 0. The potential difference between A and D is the value of the voltage source. Remember, potential difference is a definition of voltage. Notice that the potential A at the two red dots are the same value, and the same with potential point at D, are both at a value of 0. The potential will start at some value at point A and will drop in value after each resistor until it reaches 0 at point D. If resistors 1, 2, and 3 are different values, then the potential difference or voltage across each resistor will be different too. However, in special cases, if all three resistors are the same value, then the potential will drop evenly after each resistor, thus resulting in the same potential difference or voltage across each resistor. But that only applies if all three resistors are the same value. The sum of the voltage across each resistor will equal the value of the battery voltage source. In the equation you also see that Ohm's law is applied. V equals IR. Now here is an important equation to write down for resistors in series. The total resistance of a circuit is called equivalent resistance. With resistors in series, you can calculate the equivalent resistance by simply adding the values together. Having the equivalent resistance is the same as having the resistors 1, 2, and 3 in series. Now the second term that you need to know is resistors in parallel. When resistors are in parallel with each other, the current is drawn from the battery and runs into an intersection, or that is more properly known as a node. When a current runs into a node, it will split among the different paths. And in this example, the current will split among 3 different paths. It's like a river at a fork. Some of the water goes down one path and the rest will flow down the other path. Once the 3 currents, 1, 2, and 3, runs into node B, the values will add up together to obtain the original value I. Now, since the resistors are in parallel, the potential difference or voltage across each resistor is the same because A represents one value of potential and B represents the value of 0 potential. So for resistors in parallel, the voltage across each resistor is the same, but the current through each resistor is different, unless the resistors in parallel happen to have the same value. The current would then be split up evenly among the 3 resistors. The total current can be found by using Ohm's law with equivalent resistance or by adding up currents 1, 2, and 3. Now here's another important equation to write down. This equation is used to calculate the equivalent resistance for resistors in parallel. Okay, I think we're finally ready for an example. You have a 10 ohm and a 15 ohm resistor. What is the smallest and largest equivalent resistance that you can make with these 2 resistors? The largest resistance can be created by having the resistors in series. Using the equation for calculating the equivalent resistance with the resistors in series, we have 25 ohms. For the smallest equivalent resistance, the resistors are in parallel. And with using the equivalent resistance for resistors in parallel, we get 6 ohms. Now, please take a careful look at how this is done mathematically to calculate the equivalent resistance for parallel. Now in this example, we have light bulbs that are in the figure below that are identical. Which configuration do you think produces more light? And then for part B, which way do you think the headlights of a car are wired? Now previously we just saw that resistors in parallel will produce the smallest equivalent resistance. Well, the smaller the resistance, the more current that will be drawn out from the battery because there's less obstacles or boulders in the river. So more current equals a brighter light. Now, for part B, in parallel, because if one bulb goes out in a parallel circuit, the circuit is still a complete loop, whereas if it were in series, if one bulb goes out, the loop is no longer complete.